Good afternoon, everybody. That was quick. I'm Jerry Cohen, the president of Carnegie Mellon, and it's my great pleasure to welcome you here to this Buhl Lecture. You know, when we have long-serving administrators, especially successful ones, I think we sort of forget that they had a life before they became an administrator. Present company excluded, of course. And I'm talking about Fred Gilman, your dean, our dean, who is a distinguished physicist and had a long career as such before he came to us as an administrator. And I want to take the opportunity to introduce Fred, rather than him just getting up here and introducing our speaker. Fred received his PhD at Princeton, and after a postdoc at Caltech, he joined the Stanford faculty and SLAC, where he was for 20 years, having established himself as a leader in his area of physics. Fred left Stanford to head up the physics research division at the superconducting supercollider. And if there was a silver lining to the cancellation of the SSC for Carnegie Mellon, it was certainly the fact that Fred came to join us after the demise of the SSC in 1995. In those 16 years, he's provided outstanding leadership to this university as head of the physics department and now as dean of the Mellon College of Science. He has many things in his background which are distinctive, but the one I'll just mention is his time as chair of HEPAP, the High Energy Physics Advisory Panel, from 1999 to 2006, during which he provided national leadership to go along with the local leadership he was providing to us. Who better to introduce to you the Buhl Lecturer than the Buhl Professor of Theoretical Physics, Fred Gilman.
Thanks, Jerry, for the introduction. As Buhl Professor of Theoretical Physics, I'm very pleased to welcome you to the 2011 Buhl Lecture. This is the 16th lecture since the series was reinstituted in 1996. I'm thrilled to have been able to bring Scott Aaronson to Carnegie Mellon today to give this year's Buhl Lecture. Scott received his PhD in computer science at UC Berkeley, did postdocs at the Institute for Advanced Study in the University of Waterloo before he went to MIT, where he's associate professor of electrical engineering and computer science. He works on some of the deepest problems in mathematics, particularly in the theory of computational complexity, asking what are the fundamental limits on what can be efficiently computed. He's the creator and zookeeper of the online Complexity Zoo website. I confess to still be in the petting zoo, wandering around, a little mystified. And also, he writes a very popular blog, www.scottaaronson.com/blog, which is called Shtetl Optimize. Now, those are two words that you wouldn't even usually put in the same sentence, let alone together in a title. As with almost all the Buhl Lectures, he's not only a superb researcher, but a great teacher, as you'll see today, and it gives me great pleasure to introduce the 2011 Buhl Lecturer, Scott Aaronson, who will take us on a tour of the mathematical world of complexity, speaking on quantum computing and the limits of the efficiently computable.
Okay, well, thank you so much to Fred and to everyone else. It's always a pleasure to be here at Carnegie Mellon. So, you know, to be honest, when I was invited here, I didn't understand the scope. I said, sure, I'll be happy to, you know, talk to, I thought, for a few physicists. I didn't realize I'd be in this jungle here or something, you know. You know, feels like maybe this is like a royal wedding, okay? But so look, I wanted to tell you something about quantum computing and the limits of the efficiently computable. This here is an actual photo of a quantum computer. Well, I did a Google image search for quantum computer, and this is what came up. All right. So the starting point for this talk is that there are certain technologies that would be really great if we had them. I would certainly love them, and yet we never seem to see them. Okay, and you can ask why not. The first one of these is warp drive. Okay, we've been watching it, in science fiction. Where is it? Okay, we're waiting. So. The second is the perpetual motion machine. Okay, this is clearly the only long-term solution to the world's energy problems. Okay, again, why we can describe it. Why don't we see it? Okay, and now the third is maybe a little bit less common, but I think just as interesting. It's what I'll call the Uber computer. Okay, so this is a computer that sort of instantly answers any well-posed mathematical question that you can put to it. All right, I'm not even going to talk about asking it the meaning of life or something like that, okay? I'm just asking that it should instantly answer, any mathematical question, okay? And, despite what it may sometimes seem like, we don't have that. Even the fastest computers on Earth, if you ask them some problem about finding the proof of some hard theorem, they may not be able to do it within the entire lifetime of the universe. Okay, and in fact, this is why there are still human mathematicians today. Okay, so now when we look at these three devices, we can ask, why do they seem to be impossible? Why do we not have them? Is it just limitations of engineering that no one has put cranks and levers together in the right way to build them? Well, at least in the first two cases, we have a pretty good idea that the answer is no. That in fact, the impossibility of these devices is linked to some of the deepest principles in physics. Okay, so in the first case, we don't have faster than light travel or communication because special relativity tells us that the structure of space-time just doesn't permit that. If you were to go faster than light, you're also going backwards in time. Okay, in the second case, we don't have perpetual motion machines because they would violate the second law of thermodynamics. Okay, so what about the third case? Is the third case just sort of a technological accident, or is there also some fundamental physical reasons why we don't see Uber computers? Okay, so in this talk, I'm going to try to convince you that sort of the limits of computation are also, like these other two examples, telling us something important about the physical world. Okay, and that therefore there's something that not just computer scientists but also physicists should be worried about. And in fact, that maybe we can even turn it around and use it to say something new about physics. Okay. All right, so this talk is going to require like a 5-minute crash course in some of the fundamental concepts of my own field of computational complexity theory. Okay, so I'll go quickly through this, okay, but basically in theoretical computer science, in the field of complexity theory, we're interested in problems and in how fast you can solve them or what kind of resources you need to solve them. Okay. Now, what do we mean by a problem? Well, the standard example would be just some infinite sequence of yes or no questions. Okay. So, for example, I would give you a flight map. And I would ask you, is every airport reachable from every other one in 5 flights or less? Okay, so, a simple question. Now, an important point, any particular map is just an instance of the general problem. Okay, the set of all possible maps, now that's a problem. Okay, computer scientists are a little bit, snobbish about this. Okay, give me an infinite family of things. Okay, that's a problem. Okay, and so, what you'd like is some general method or algorithm or procedure that solves any given instance of the problem. Of course, for this or that particular instance, you may find some clever way. Maybe you can even do it on pencil and paper. But, you want a general procedure that you could feed to your computer that always works. Okay, now the size of an instance usually just means the number of bits needed to write it down. Okay, or you can think interchangeably, like in this example, the size of the instance is going to be roughly the number of cities. Okay, and now we would like algorithms that solve these problems, and usually, there's some trivial way to solve it, which is that you could just enumerate all of the possibilities. Okay, but we don't want that. We want some way to solve the problem efficiently. Okay, now, so what do we mean by efficient? We have this notion called polynomial time. An algorithm is polynomial time if it uses a number of steps that grows basically like the size of the instance to some fixed power. Okay, so it could grow like n or like n squared. That's also okay. It could even grow like n to the 100, which doesn't sound very efficient, but it doesn't tend to come up very often in practice. Okay, what it shouldn't do is grow like 2 to the n. Okay, that's exponential growth, and that's what we don't want. Okay, so now, Fred mentioned this complexity zoo. It has about 500 different classes of problems solvable with different resources, but maybe the most fundamental one that started it all is called P. Okay, it's polynomial time. This is simply the class of all problems for which there's a deterministic polynomial time algorithm on a conventional computer that solves every instance. Okay, so you can think of it roughly as the class of all feasible problems. Okay, so now the second class we should mention is called NP. Non-deterministic polynomial time. Okay, now, I have to tell you, I envy the physicists because, even if people don't understand what they're talking about either, at least they have awesome names for things, like quark, supersymmetry, black hole. Computer scientists, we're stuck with P and NP, okay? But it really is just as interesting, okay? So what is this NP? Okay, so NP is basically just the class of all problems for which you can efficiently recognize an answer if it's given to you. Okay, so if the answer is yes, there should be a short proof that it's yes, which can be checked in polynomial time. Okay, so it might be very hard to solve the problem, but at least you can recognize the answer. A classic example of an NP problem would be factoring a giant integer, like that one here. Okay, so I could ask you some yes or no question, like does this number have a prime, or have any factor, let's say, ending in 7? Okay, and now, if I gave you this problem and asked you to solve it, it might take an astronomical amount of time. You could say, well, does 3 go into it? No. Does 5 go in? No. Does, you'll be doing that for a while. Okay, but on the other hand, if I gave you the factors, then, you could multiply them together and say, oh, well, I guess it did have a factor ending in 7. Okay, that wouldn't be as hard of a computation. Certainly not for a computer. It can multiply numbers pretty quickly. Okay, so, all right, so now there's this concept of an NP-hard problem. A problem is called NP-hard, basically if it captures the difficulty of every NP problem. So basically these are the problems that if you had a way to solve them, then you could use that to solve all of the NP problems. Okay, now the final concept is a problem is called NP-complete if it's both NP-hard and it's in NP. Okay, so basically the NP-complete problems are the hardest problems for which it's easy to check the solution. Okay? So, you have to think about that for a bit. But this sounds like just playing around with words. But the profound discovery that people made in the 1970s that really started this whole field of complexity theory, in its sort of modern incarnation, was that a huge number of practical problems that people care about, actually belong to this NP-complete class. Okay, so problems from physics, from economics, from biology, from, all kinds of fields. Now one famous example is what's called the Hamilton cycle problem. Okay, so here I would show you a map like this with a bunch of cities, the yellow dots, and some are connected to each other. And I would ask you, is there a tour that visits each city exactly once? Okay, now in this case there is one. It's that. Okay, and if I show it to you, then it's not hard to check it and say, yes, indeed, it solves the problem. Okay, but if I don't show you the tour, then you may have to think about it. And as the number of cities increases, the difficulty of the problem may increase a lot. Okay, it's like, or think of solving a jigsaw puzzle. That's another example of an NP-complete problem. Okay, or Sudoku is another. Okay, and also, many other problems of more economic importance. Okay, airline scheduling, things like that. Okay, so just to give you the brief layout of the world. So at the very bottom we have P. Sort of, think of all of the problems for which we know a feasible way to solve them with today's computers. Okay, so, and there's lots and lots of non-obvious things in here, like testing whether a number is prime or composite, linear programming, lots of interesting stuff. Okay, but then above it, there's this whole class of problems, NP-complete ones, for which no one knows of any efficient way to solve them. Most of us believe that there isn't one. Okay, this is also a huge class containing lots and lots of practical problems. And then certainly there's plenty of stuff that's even harder than NP-complete. Okay, one famous example is the halting problem. I give you a program and you want to know whether it will ever stop running or not. Okay, and then very interestingly, there are these problems that we think lie in an intermediate region between P and NP-complete. Okay, so there are NP problems that are floating in the middle somewhere. And a famous example of that is one I already showed you, this problem of factoring large numbers. Okay, and as we're going to see, these problems that are in this intermediate region, there's not that many of them, but they're hugely important, sort of both on the one hand for cryptography and on the other hand for quantum computing. Okay? Okay, so the literally $1 million question here, and I mean, if you solve it, you actually get $1 million from the Clay Math Institute, is whether P equals NP. Okay, so in other words, can all of the problems for which you can recognize the answer efficiently, if someone gives it to you, can you actually find the answer efficiently? Okay, can you actually solve the problem efficiently? So, are the classes P and NP equal? Okay, equivalently, we want to know just can the NP-complete problems be solved in polynomial time or not? Okay, and this is a profound mathematical question. Probably the shortest proof of its importance I can give you is that it's appeared on both The Simpsons and Futurama. It's done cameos, so this is a problem which has entered the popular culture. Now the problem, as far as anyone knows, was sort of first asked actually in 1956 in a letter that Kurt Gödel, the incompleteness guy, wrote to John von Neumann. Von Neumann at the time was dying of cancer in the hospital, and Gödel wrote this letter that said, "My dear von Neumann, I hear that you're getting better," which he wasn't, but since you are, let me take the liberty of troubling you with a mathematical problem. And he then asked a problem that today we would immediately recognize as the P versus NP problem. Okay, he asks sort of, is there a general decision procedure that, given a mathematical question, will tell you whether it has a proof of n symbols or less? Okay, we knew from the great work of Gödel and Alan Turing in the 1930s that there can be no general decision procedure for mathematics. It tells you whether a statement has a proof or not. What about just a proof of n symbols or less? Okay, this is clearly a finite problem. In principle, you could just enumerate every possible proof one after the other and see if any of them worked. Okay, but, is there actually an efficient procedure? One that takes a number of steps that grows like n or like n squared, let's say, instead of like 2 to the n power. Okay, that grows algebraically instead of geometrically. Okay, and he says if such a procedure existed, it would have consequences of the greatest magnitude. it would mean that the mental effort of the mathematician could be completely replaced by machine. And then he has a little asterisk, and he says, apart from the postulation of axioms. Okay, so basically, here's what he's saying. So P versus NP is recognized as one of the greatest unsolved problems in mathematics, right? It's one of these 7 Clay problems alongside the Riemann hypothesis, the Poincare conjecture, which was solved almost a decade ago by Grisha Perelman, and several others. Okay, but in my opinion, P versus NP is actually manifestly the most important of the 7 problems. It's the greatest mathematical problem. And the argument for this is simply that if P were equal to NP, then probably you could not only solve that one problem, but also the other 6. Okay? Because you would simply program your computer to find the proofs for you. Okay? So this is a math problem, but it's also a problem about the nature of mathematical reasoning itself. Okay, so this is the P versus NP problem, why it's important. Okay. People have been asking this question for, more than 40 years now. I should tell you that I think a lot of, there's been a lot of progress. There have been some breakthroughs proving things that are, nowhere near P not equal to NP, but some sort of baby results. People are, we know more than we did, than people did in the 70s, right? But it's a tremendously difficult problem. Now, because of this blog that I write, I get solutions to this problem in my inbox, I would say every other week or so. Either that they're equal or that they're not equal. In a couple cases, they were accompanied by death threats if I didn't publish them. Okay, but the most recent serious attempt, some of you may have seen, was this summer. A guy named Vinay Dialalekar, who had actually what looked like a serious attempt at a proof, and I was on vacation at the time. People were flooding me with emails. Is this correct or not? I could tell that it almost certainly wasn't correct, but I didn't know where a mistake was, so I said, look, if he gets this $1 million prize, so I'll supplement it by $200,000, okay? And I thought that couldn't possibly be controversial. I was wrong about that, but in any case, the long story short is that I didn't have to give up my house. The problem is still open, is still extremely difficult, and we hope that someday mathematics will have advanced to the point where we can tackle questions like this one. But in the meantime, we can continue to think about P versus NP as a purely mathematical question, which it is, and that's great. Okay, but there's also a different perspective that we can take on it. Okay, and that's that there's actually a very important presupposition that sort of underlies the P versus NP question, or why do we ask the question in this particular way and not some other way? Okay, and that presupposition is called the extended Church-Turing thesis. Basically, this is the thesis that this theoretical model of a computer that we've been working with since the 1930s, which is called the Turing machine, is really the right model for what can be computed in a reasonable amount of time in the physical universe. Okay, so there was an original Church-Turing thesis which said that the Turing machine captures if something can be computed in any amount of time in the physical world, then it can also be computed by a Turing machine. Okay? And that, it's fair to say, I think that there's been no serious challenge to that thesis. Not even quantum computing does anything to challenge that. Okay, but then there's the extended version, which says that if something can be efficiently computed in polynomial time in the physical world, then it can also be computed in polynomial time by a Turing machine, either a deterministic or maybe a probabilistic one. Okay, and that thesis has always been on shakier ground. And in fact, you're going to see shortly that quantum computing poses a serious challenge to it. Okay, so we could ask, okay, just in general, how sure are we of this thesis? What are the challenges to it that have been put forward over the years? All right, so let's start with sort of the challenges that have been to this extended charge Turing thesis that computer scientists have sort of kicked around since the 1970s or so. So my personal favorite is that you could violate the extended charge Turing thesis and exceed the computational capacity of a Turing machine using a tub of soapy water. Okay, so how exactly would that work? Okay, so what you would do is you would take two glass plates and you would put pegs between them, in whatever configuration you wanted. Okay, and then you would take this thing and dump it, just hold it into a tub of soapy water, and you would take it out, and what you see is some soap bubbles which will form. Okay, and in general, bubbles like to reach a minimum energy configuration, and this more or less corresponds to minimizing the total length of bubbles, connecting the pegs together. Okay, and so in other words, if the bubbles really relax into their lowest energy state, then they ought to relax into what computer scientists and mathematicians know as the minimum Steiner tree. Okay, so this is the minimum total length of line segments connecting a bunch of points in the Euclidean plane, where those segments could also meet at intermediate points. Okay, so I've shown an example here. Now, the interesting thing is that this minimum Steiner tree problem is known to be NP hard. Okay, and yet nature seems to solve it. You just, dip these pegs in the soapy water, right, and just let nature find the lowest energy state. Okay, so there was a discussion of this on the internet some years ago, and people made the point that I think was important here, which is that, well, systems in nature, can be amazing in trying to find solutions to optimization problems, but we also know that they can get stuck in local minima. Okay, so for example, if you had a rock on some crevice on a mountainside, it could reach a lower state of potential energy by rolling up first and then rolling down, and yet it's rarely observed to do that. Okay, so why not? Why shouldn't things be the same with these pegs, right? There might be some, completely optimal way to connect the pegs together. But if you've, put together a system of pegs such that the minimum Steiner tree connecting them together encodes a proof of the Riemann hypothesis, which in principle one can do. That's what NP completeness tells you, right? Then, why on earth would you expect nature to find that optimal configuration instead of one of the thousands and thousands of suboptimal ones that it could happily, get to? Okay, and then, some other people were arguing with this, and they said, well, this is just really this academic computer science party line. I bet none of you who are saying this ever actually went and did the experiment. So this was my only foray in my life into experimental physics. So I went to the hardware store, did it. It looks it's very cool with like 5 or 6 pegs. You should actually try it. It's nice. But then, you start adding more pegs, 7 pegs, 8 pegs, and indeed you can find that sometimes it does not reach an optimal configuration, okay? Sometimes you even have cycles, which we know actually can't be optimal. It has to be a tree. Okay, so, all right, so much for this. There are other approaches that people have put forward for trying to solve NP-complete problems in nature. One is that if you look at proteins, proteins are really amazing. They somehow fold very quickly into some low energy state. And if you formalize this problem in the right way, you can actually show that the problem of finding the minimum energy folding configuration for a protein is, again, NP complete. Okay, and yet again, the proteins do it. Okay, but again, the resolution is that proteins are actually specifically evolved over billions of years so that the minimum energy configuration will be easy to find. Okay, so that it will be an easy computational problem. If you designed a protein where it's a hard computational problem, then there's sort of no very good reason to expect it to reach its minimum energy state. Okay, and in fact, even in nature, we do sometimes see proteins that fold into the quote-unquote wrong configuration. So these are prions, for example, the agent of mad cow disease. Okay? People have also proposed using DNA computers, which would be this massively parallel, way of trying to solve these hard optimization problems. But from our perspective, DNA computer is really sort of a very, very parallel classical computer. So in other words, the amount of DNA that you need to put in your test tube will increase exponentially with the size of the problem that you're trying to solve until you have to convert the whole Earth into DNA or something. Okay? So this, again, is not a scalable solution. All right. But what about quantum computing? Okay, you knew it was coming at some point. Okay, so this is was an amazing new idea in I guess both in physics and in the theory of computation that got widespread attention starting around 17 years ago. And what's the idea? Well, the idea is to exploit sort of quantum mechanics, which has been our fundamental framework for almost all of physics for almost 90 years now. You hear a lot of things about quantum mechanics, that it's about light being both a particle and a wave, that it's about the hydrogen atom having these discrete energy levels, that it's about randomness, this and that. From a computer scientist perspective, quantum mechanics is simply a generalization of probability theory, okay, where instead of probabilities, which are non-negative real numbers, we replace them by these numbers called amplitudes, which can be complex numbers. And so in particular, they can have minus signs in them. Okay? And for whatever reason, nature seems to prefer things that way. Okay, so, once all of the quantum phenomena that people talk about, like entanglement and interference, and so on, they're all just logical consequences of this one change that you make to foundations of probability. Okay, so contrary to its reputation, quantum mechanics is actually unbelievably simple once you take the physics out. Okay. Okay, so in particular, this perspective lets us easily talk about what is the idea behind quantum computing. So in the 1980s, Richard Feynman and David Deutsch and several others noticed something very interesting, that if you have a quantum system with, let's say, n particles, then in order to describe the state that system is in at a given time, you seem to need not just n numbers or 2n or 3n, as in classical physics, but actually something like 2 to the n power, okay? Because you need to give one of these amplitudes, these, sort of minus sign probability things, to every possible configuration that all n of the particles could be in. Okay, and the number of such configurations increases exponentially with the number of particles. Okay, now this is a mind-boggling fact about physical reality. I mean, it took a while for this to really sink in, but I think in retrospect, this is really arguably the central or one of the central facts about quantum mechanics. And in particular, what it's a huge practical problem for people who try to simulate quantum physics on classical computers. It means you have an exponential slowdown. Okay, what Feynman, and Deutsch and the others noticed is, hey, maybe you could turn that around. Why not build your computer out of quantum mechanical elements? And then, you won't have that exponential slowdown problem. Okay, but then what you've really built is a fundamentally new kind of computer, one that could, in principle, solve some problems exponentially faster than any of the computers that we use today. So then you could ask, what else is it good for besides, just the task of simulating quantum physics, which is sort of what it could do in its sleep. Okay. So yeah, I like to describe quantum computing as the power of 2 to the n complex numbers working for you. Okay, now as I guess is well known, actually building a scalable quantum computer turns out to be damn hard. And the basic reason is that once a quantum computer state is measured, then it reverts to being classical. Okay, you sort of, a quantum computer is in what's called this superposition with all of these different amplitudes for all the different possible states that it could be in. Okay, but once you measure it, you force it to make up its mind. Okay, and then it's just in one state. And you don't get to measure twice. Once you measure, you get an answer out, then it's gone. Okay, so and this applies not just for measurements that you would do, but for measurements that are implicitly performed by any stray particle that may happen to pass through your system. Okay, and so what this means is that to build a scalable quantum computer, you would have to keep it extremely well isolated from the rest of the world, but at the same time be able to go in and actually do the computation. Okay, so it's those twin requirements that are sort of the reason why we don't have scalable quantum computers yet. Okay, what's been done after sort of a decade of work and sort of more than $1 billion spent by research groups all over the world is that a quantum computer has, with high probability, shown that 15 equals 3 times 5. Okay, 21 might be next, but scaling it up is extremely hard because of this decoherence problem. Okay, but on the other hand, no one has been able to articulate any clear reason why it should not be possible in principle. Okay, some computer scientists will tell you that it must not be possible because if it were possible, then you could, quickly factor huge numbers and solve these hard problems. That's sort of a circular argument. Okay, but so I think that we're really in the situation maybe of Charles Babbage in the 1830s, right? We have the theory, it ought to work, but in his case, it took more than a century for the transistor to be, the vacuum tube or the transistor to be invented, and for the technology to catch up with the theory. In this case, we have no idea how long it's going to take. Fortunately, that won't concern me for this talk. I'm going to talk about what could be done in principle. And if with a quantum computer, and if you don't like it, I think I personally tend to think that we will see, either practical quantum computers or what would be even more interesting than that, a reason why building a quantum computer is impossible. One or the other, in any case, long before we see a test of string theory, for example. Okay? Okay. So, an important point. So I say journalists beware, because this is something that almost every popular article about quantum computing ever written has gotten wrong. Okay, and it got to the point where I started a whole section on my blog, which was called "Speaking Truth to Parallelism." Okay, because every writer seems to want to describe a quantum computer as this massively parallel classical computer that could just sort of compute all of the possible answers in parallel and then instantly pick out the best one. Okay, and in fact, just this week there's a whole long article about quantum computing in the New Yorker. Maybe some of you have seen it, but it just repeats the same mistake that some of us have been trying to correct for 12 years. One mind at a time. In this case, a couple hundred, I guess. But so a quantum computer, once again, it has this exponential number of states that are all, so you have this exponentially long list of amplitudes that are describing your quantum computer state. Okay, which is an amazing fact, and it is very different from anything in classical physics. The problem is that as soon as you measure the quantum computer, as I said, you only get out one outcome. Okay, and therefore, so you could say, look, it's like, I don't know what state the machine is in, and then I look, and then I do know. What's magic about that, right? So if there's any hope of getting a speed up by this type of computer, of doing something which a classical computer cannot do, then everything rests on one fact, which is that amplitudes can interfere with each other. Okay, so of all of the different sort of paths that could lead to a given answer, so, some can have positive amplitude, others can have negative amplitude. If that's the case, then those amplitudes will cancel each other out, with the result being that that answer will, possibly not be observed at all. Okay, that is the thing about quantum mechanics that makes it different from just classical probabilities or classical randomness. Okay, and all of the hope of solving problems more quickly with a quantum computer, rests on exploiting that type of interference in some clever ways to solve certain specific problems faster than we know how to solve them with today's computers. Okay, now this idea was around since the 80s, but no one knew what it was actually good for. Okay, so no one knew how to actually create this pattern of interference that would reveal the solution to some hard computational problem. It sounded like a very tall order. Okay, it wasn't obvious whether quantum computer would be good for anything at all. Okay, so that's why the first thing to do was for sort of computer scientists to sort of get a hold of this and, give it a sequence of capital letters. Okay, so this was my advisor, Umesh Vazirani, and his then student, Ethan Bernstein, define a quantum generalization of P, of polynomial time. This class is called BQP, for bounded error quantum polynomial time. Okay, and basically this is just the class of all of those problems which are feasibly solvable by a quantum computer. Okay, again, using a number of quantum operations that increases only polynomially with the problem size. Okay, and you say, look, everything is probabilistic in quantum mechanics, so we'll only insist on, say, a 90% chance of getting the right answer. Okay, if you're not happy with that, just repeat the computation several times, and you can boost that to a 99.9% confidence, or however great you want. Okay, that's what the B is saying. Okay, so once we had BQP, we could then sort of actually think about it like mathematicians and ask the question of how great is its extent? What does it contain? Okay, and here a profound breakthrough happened in 1994 when Peter Shor, who's then at Bell Labs, now at MIT, showed that the problem of factoring an integer into its prime factors, which I mentioned to you before, is in BQP. Okay, so he found an extremely clever way to exploit interference in order to actually find the period of periodic functions, something called the quantum Fourier transform. Okay, and it was known since the 70s that if you could find the periods of periodic functions, then you could use that to factor numbers. Okay, now why do we care about factoring numbers? Is it because, we're mathematicians, we love, number theory and primes? Well, sure, but it's also because most of the world's cryptography today happens to rely on the assumption that factoring huge numbers is a hard problem. Okay, if you ever order something from Amazon or eBay or whatever, the encryption that your web browser is using to protect your credit card number depends on this assumption that factoring is hard. Okay, if Shor showed that if a quantum computer is built, then that assumption fails. Okay, so this was one reason why people got interested. So just to complete our world map, so I told you before that factoring is one of these problems that seems to be floating in an intermediate region between P and NP complete. Okay, so what Shor showed is that BQP, which is the quantum generalization of P, actually snags factoring. Okay, it's, sort of sufficiently larger than P that it actually captures this very, very practically interesting problem of factoring huge numbers. Okay, now I drew BQP as not encompassing the NP complete problems. Okay, this is a big open problem to this day. We don't know whether BQP contains the NP complete problems or not. Okay, so remember, I told you factoring is neither known nor believed to be NP complete. In fact, we have very strong evidence that it is not NP complete. Okay, now today, many of us believe that BQP does not contain the NP complete problems. In other words, that there is not a fast quantum algorithm to solve all of these NP complete problems. Okay, not surprisingly, we can't prove that it doesn't. Okay, there's very little that we can prove, and there's in this field. There's a lot that we can conjecture. Okay, so I mean, look, we don't even know if classical computers can solve NP-complete problems in polynomial time, right? That's the P versus NP question. So if we can't even prove that P doesn't contain NP, then how on earth are we going to prove that BQP doesn't contain it? Okay, so yeah, so it's an open problem. And on the other hand, certainly no one knows how to use quantum interference to solve NP-complete problems. Okay, and in fact, we have some evidence that if it's possible at all, it's going to be extremely hard. In particular, there's a great result of Bennett, Bernstein, Broussard, and Vazirani from '97, which says that in some sense quantum magic will not be enough to solve NP-complete problems. Okay, so what they showed is that if you were to throw away the structure of an NP-complete problem and just envision it as you have this abstract space of 2 to the n possible solutions to some really hard problem, okay, and for each solution, the only thing you know how to do is to just feed it to some machine that tells you is this a valid solution or is it not one. Okay, let's say just one solution out of all these 2 to the n is a valid one. So you're looking for a needle in an exponentially large haystack. Okay, then what BBBV showed is that you're going to have to ask a lot of questions to that haystack. Okay, you're going to have to spend a lot of time sifting through the haystack. Now that's obvious if you're a classical person, right? If you've got a needle in a haystack of size 2 to the n, well, then probably it's going to take exponential time. That's a lot of hay. Okay, but what if you're a quantum computer and you can ask questions about every possible location in the haystack in superposition, and then do some coherent quantum transformation on that, then could you somehow magically, just converge on the needle in like 1 or 2 steps? Okay, what they show is that that's actually not possible, and that the best that you can do in that kind of situation is you can find the needle using a number of steps that scales only like the square root of the number of pieces of hay. Okay, you can get a quadratic speed up over what a classical computer could do. So for example, if there were 2 to the 10,000 pieces of hay, now you don't need 2 to the 10,000 time, you merely need 2 to the 5,000 time. Okay? Okay, so BBBV proved that that's the best possible, and then actually after that, Love Grover showed that actually that square root speed up can be achieved. Okay, so this gives the second most famous quantum algorithm after Shor's factoring algorithm. It's Grover's search algorithm. Okay, and Grover's search algorithm was actually proved to be optimal before it was discovered to exist. Okay, so for this general type of problem, this square root speed up is the best you can hope for. It's still impressive. It's still something amazing and cool, but it's not exponential. Okay, it doesn't turn an exponentially hard problem into a polynomial one. Okay, so what this is telling us is that if there is some way to solve NP-complete problems efficiently using a quantum computer, then you're going to have to somehow exploit the structure of the problems. Okay, just as a classical algorithm would have to. So you're now in a regime where, we sort of, there's lots of things you could try. No one really knows what to do. Okay, now there's one quantum algorithm that's been put forward, basically, that does attempt to exploit the structure of these NP-complete problems in order to solve them faster. This is called the quantum adiabatic algorithm. Okay, and it was proposed by Ed Farhi and Jeffrey Goldstone and several of my other colleagues over in the physics department at MIT 11 years ago. Okay, and they actually developed this algorithm by using their intuition from physics and from condensed matter systems, for example. And they said, look, you can start out, applying some Hamiltonian. Don't worry what that is. I myself only learned, after I'd been in the field for some time. It's some, physical operation, okay? And it has, and there's some state some lowest energy state, that if you apply this operation, h sub I, to a system, then your system likes to be in its lowest energy state. Okay, then you can have another Hamiltonian, call it h sub f, whose lowest energy state actually encodes the solution to an NP-complete problem. Okay, it's not hard to design one of these Hamiltonians. There's, just some set of physical interactions between a collection of particles. That's all it really means, such that the lowest energy configuration for those particles to be in is the solution to an NP-complete problem, like the Hamilton cycle, like the satisfiability, something like that. Okay. Now there's a theorem that's been known since the 1920s called the Diabatic Theorem. And what it says is that if you start out applying this Hamiltonian with some easily prepared ground state, and then if you just slowly vary the Hamiltonian over time until it becomes h sub f, then as long as you vary it slowly enough, the ground state at each instant of time will simply be that the system will just be in the ground state of whatever Hamiltonian you're currently applying. Okay, so you can just sort of drag the ground state along until by the end it will be in the ground state of h sub f, and you'll thereby solve your NP-complete problem. Okay, so this was an amazing observation, an amazing connection between theoretical computer science and condensed matter physics. Okay, but then the key question that is left is, okay, so how slowly do you need to schlep the thing, right? If the thing is going to stay in the ground state and not jump to some, local optimum, to some other state. Okay, so it turns out that the speed with which you need to drag the thing depends on actually the spectral gap of the Hamiltonian. So as you vary it, this h sub I is described by some matrix, called h sub t, and the running time, the time for the algorithm is scales like the inverse of the gap between the smallest and the second smallest eigenvalues of that Hamiltonian. Okay, and so people looked at, so now the question was, how small can this gap be? Okay, the smaller the gap, the longer you've got to run the algorithm for. And what was eventually discovered is that if h sub f corresponds to certain hard instances of NP-complete problems, then this gap may need to be exponentially small. Okay, so you look at the graph, it looks like the two lines are crossing each other, but they're not quite. There's this tiny little gap where they almost kiss each other, but not quite. Okay, and it's just because of that one little point that you've got to run the algorithm for exponential time. If it wasn't for that, you would be solving an NP-complete problem in polynomial time. Okay? But the amazing thing about this is that if you believe already that NP-complete problems are hard, then you could actually make a prediction about the behavior of condensed matter physical systems. You could say that this gap has to decrease exponentially, and in fact some of us did say that. We were kind of going out on a limb because we didn't know anything about physics. Okay, but we ended up being right. So and actually, Farhi told me that he's spoken to condensed matter experts and said, based on all of your experience with these physical systems, do you think the spectral gap will decrease polynomially or exponentially as the size of the system is increased? And this expert, I forget the name, some guru in the field, said, I think it will decrease exponentially. And Farhi said, well, why do you say that? And the guy said, because otherwise your algorithm would work. Okay, so this is an example of how you can sort of, if you believe that, these problems are probably hard, then, you could sort of turn that around and sort of say, what are the implications for physics? Just like, if you already believe that you can't communicate faster than the speed of light, then that in turn implies other things about the laws of physics. Okay? All right, so what else could you do if you wanted to solve, if you really, really wanted to solve these NP-complete problems and, put mathematicians out of business? Okay, so now I'm going to tell you about some speculative changes to the laws of physics that would enable NP-complete problems to be solved. This is the fun part of the talk. Okay, the first example is, so you look at the Schrodinger equation, which is the governing equation of quantum mechanics, and this an amazing thing about this equation is that it's exactly linear. It's a linear differential equation. Okay, but people have speculated, like Steven Weinberg and other physicists, for a long time about what would happen if you inserted tiny nonlinear terms into the Schrodinger equation, maybe too tiny to have been detected yet. Okay, and it was realized that all kinds of crazy things would happen. For example, you could then communicate information faster than light. Okay, but in '98. Abrams and Lloyd pointed out that another crazy thing that would happen in such a scenario is that then quantum computers really would be able to solve NP-complete problems in polynomial time. Okay, and I can explain how it works with just a picture. So it's very easy to create a quantum state, let's say of one quantum bit, one qubit, that will be pointing in some particular direction. Quantum state is just a vector. Okay, so let's say it'll be pointing this way if there are no solutions to some NP-complete problem. And if there's one solution, then it'll be pointing almost the same way, but just sort of exponentially a small amount up. Okay? So now, of course, the problem in conventional quantum mechanics, so yeah, you can make these states, but if you wanted to actually distinguish them from each other, then you would need to repeat the experiment an exponential number of times. Okay, because these states are so close that when you make a measurement, almost always you're going to get the same answer. Okay, you're only exponentially unlikely to even see the difference between these two. Okay, so this doesn't give you a practical way of solving NP-complete problems quantum mechanically. Okay, but Abrams and Lloyd pointed out, well, what if the Schrodinger equation were nonlinear? Okay, in that case, there could be transformations on states that would not have to preserve the angle between pairs of states. And so what you could do is sort of have these states and then just sort of gradually pry them apart. Okay, you could apply some nonlinear transformation sort of very generically that just sort of increases the angle between them until they're orthogonal or almost orthogonal, in which case they can be easily distinguished by a measurement. Okay, so, now one conclusion you could draw from this is, wow, that's awesome. We should go out and look for these nonlinearities because then we can solve NP-complete problems. Okay, another conclusion you could draw is maybe this is actually providing us an additional explanation as to why the Schrodinger equation is linear. Okay, now one of my personal favorites is if quantum computers are not going to do it, then how about the relativity computer? Okay, now the idea here is an extremely simple one. You would start your computer working on some incredibly hard problem. Doesn't even have to be an NP problem, some really hard calculation. Then you leave your computer on Earth. Okay, then you board a spaceship which is traveling at very close to the speed of light. Okay, then you come back to Earth. Now billions of years have passed in Earth time. All of your friends are long dead. Civilization has collapsed, but you've got the answer to your NP-complete problem. Okay, so what's the problem with this? Why don't people try it, right? So, all right, well, I think there's actually something to say about this. Which is, you can say, all right, that sounds kind of silly, but no, seriously, why doesn't it work? What goes wrong, right? And actually, if you think about it enough, I think that the answer to that question has to do with the amount of energy that you would need in order to accelerate sufficiently close to the speed of light. Okay, what you can show is that to get an exponential speed up, you would actually have to accelerate, so much that that there would be only an exponentially small difference between your speed and that of light. Okay, to do that requires an exponential amount of energy, which then implies that your fuel tank or whatever is powering your spaceship, it probably ought to be exponentially large. Okay, so then you're again needing to spend exponential time, just to build the tank, right? Or for the fuel from the far part of the tank to affect you. Okay, and so, again, you're, needing exponential time, but just for a different reason. Okay, this is a good example of how when you look at only one or two things about the laws of physics, it can look like you have some hypercomputing power, some amazing computational power, but then when you take everything into account, it always seems to go away. Okay, another of my favorites is what I call the Xeno computer. This is also a very simple idea. Okay, you would do the first step of your computation in 1 second. You do the second step in half a second. You do the third step in a quarter second, the fourth step in an eighth second, and so on, so that after 2 seconds you would have done infinitely many steps. Okay, again, why don't people try it? Okay, well, the answer to that question is people actually do try it. They do what's called overclocking of their microprocessors, okay, where you run your chip at faster than the recommended speed. Okay, but what is the physical problem when you do that? Well, the problem is if you overclock your chip too fast, it may melt. Okay, it may actually overheat and then no longer works. So in order to safely run a chip faster, you need a cooling system. This is why supercomputers often just sort of, they may just consist of some ordinary Intel chips, but often cooled with liquid nitrogen or something so that they can be run faster. Okay, now as you want to run your chip faster and faster, you need more and more cooling. You need to cool it closer and closer to absolute zero. Okay, and now, what if you wanted to run your chip so fast that it's doing one operation every Planck time, or every 10 to the minus 43 seconds? Okay, well, no one knows exactly what happens in that case. Okay, but according to the best current physical theory, it is likely that you would need such a powerful cooling system to cool your chip to that, so that it could run that fast, that you would need so much energy to run the cooling system that you would actually exceed the Schwarzschild radius, which actually would cause your computer to collapse to a black hole. Okay? So, I really like that as sort of nature's way of telling you that you can't do something, that there's sort of, what better way could there be than for your computer and your whole office to collapse to a black hole? Okay? Okay, so once again, we see that you try to solve these NP-complete problems. You have something that looks like it's going to work, but then, in this case, sort of very deep things about the laws of physics seem to come into play and prevent you from doing it. Okay, also, maybe it won't shock you that if closed time-like curves or time travel existed, then you could solve NP-complete problems. Okay, it's a very simple way to do it. You could just read in an integer, x, say from the future. If x encoded a valid solution to, say, your NP-complete problem, then you output x again. Otherwise, you output the next solution, say x plus 1 mod 2 to the n. Okay, and now we say, what are the consistent solutions of this for this closed time-like curve? So what are the things that could be fed to the computer that will avoid a grandfather paradox, that will avoid a situation where you would go back in time and kill your grandfather, and so the universe would be inconsistent? Well, if the problem has any solutions, then the only consistent evolution is for your computer to input and output a correct solution, which nature then will have to somehow find, as if by magic, just to ensure that the laws of physics remain consistent. Okay, so, an analogy would be you go back in time and you would dictate Shakespeare's plays to him, right? And so then he would say, oh, thanks, man, that saved me a lot of effort. He'd write the plays, then they'd come down to you, then you would have them, then you would go back in time and give it to him. Everyone's happy. Okay, there's no logical paradox here. It's not like the grandfather paradox. The only paradox, if you like, is one of computational complexity. Okay, that somehow this difficult computation gets performed, Hamlet gets written somehow, without anyone ever going to the work of writing it. Okay, the same thing here with how you could solve an NP-complete problem. Okay, so I actually had a research paper about this kind of thing with John Watrous a few years ago, where we characterized exactly what you could do with either a classical or a quantum computer that had this time travel capability. We showed that it's actually larger than NP. It actually precisely coincides with a class called P-space. Okay, this is not one of the papers I'll be submitting to my tenure committee, but okay. But having seen all this, you might be led to guess what you might call a no supersearch postulate that would suggest that this would be a strengthening of the P not equal to NP hypothesis that would say that actually there is no physical means whatsoever to solve NP-complete problems in polynomial time. Not by a classical computer, not by a quantum computer, not by a string theory or a black hole computer, not by anything that anyone will ever come up with consistent with the laws of physics. Okay, so this is a very strong hypothesis. It's no longer purely mathematical, as P versus NP was, but also talks about the laws of physics. But if true, we could use it to explain other things, okay, as I've been pointing out in this talk, like why adiabatic systems have small spectral gaps, why the Schrodinger equation is linear, why we don't find closed time-like curves, and hopefully more to be discovered. Okay, but there's a question here, which is what exactly does it mean to solve an NP-complete problem? Okay, so to give you an example to illustrate the difficulty, it's been known for many decades that if you have n identical photons and you send them through a very simple setup, a network of mirrors, basically, beam splitters, then the amplitude for the photons to reach some given final configuration is given by a function which is called the permanent of an n by n matrix, in this case of complex numbers. Okay, so basically, this is because photons are bosons, one of the two basic particles in the universe, right? And bosons have these very weird statistical properties. Okay, and in particular, you've got a sum. So because these are n identical particles, right, there are n factorial ways that you could rearrange them among themselves. Okay, and each of those ways contributes some amplitude to the total, which is then a product of individual amplitudes. And so you get a function of an n by n matrix, which is called the permanent. This is actually something that computer scientists know extremely well for their own reasons. Okay, in particular, Leslie Valiant, who just won the Turing Award this year, one of his great discoveries was to show that computing the permanent of a given matrix is a sharp P-complete problem. Okay, that means presumably even harder than NP-complete. Sharp P-complete is basically the class of all counting problems. Problems that involve counting the number, not just deciding whether there exists a solution to an NP-complete problem, but actually counting the number of solutions, which we think is even harder. Okay, so then this raises a fascinating question. Okay, if the permanent is sharp P-complete, then how on earth is nature computing it? Okay, how is it that this very simple physical experiment has amplitudes which are permanents of these complicated matrices? How is nature able to keep track of this sharp P-complete function, given everything I've just been telling you about the hardness of, certainly of NP-complete problems, which are easier than these? Okay, so I think that there's a resolution of the paradox, which is instructive. Okay, and the resolution is that amplitudes in quantum mechanics are not directly observable. Okay, as I said before, an amplitude determines the probability that you're going to see some particular outcome. Okay, but if an amplitude is exponentially small, then in order to get a good estimate of the amplitude, you may need to repeat your experiment an exponential number of times. Okay, and that's really what's going on here. So I think that we should, we have to say that if, there are many systems in nature that may seem like they somehow encode the solution to some NP-complete or even harder problem, but if you can't actually get the answer out by some actual physical measurement, that one could make in principle at least, then it doesn't count. Okay? It doesn't count. So, so it's a good lesson. Now, recently, my student, Alex Arkhipov, and I studied this kind of linear optical setup, and we gave evidence that actually it does do something which is, even the observable outcomes in this experiment are already something which is hard to simulate by any classical computation. Okay? In particular, we showed that this sort of linear optical setup, which is much, much simpler, by the way, than a full-scale quantum computer, and which we hope will be easier to build than a full-scale quantum computer, can already sample from some probability distribution, which we can give evidence, some complexity theoretic evidence, is hard to sample from by any efficient classical computation. Okay, so we have no idea how to build a universal quantum computer with these resources, or how to implement Shor's factoring algorithm, or anything like that. But for this sort of made-up problem, if you really, really want to sample random matrices with larger than average permanence, then have I got the computer for you, okay? And, I hope that, that this could actually sort of put the extended Church-Turing thesis to the test, hopefully an easier way than by building a full-scale quantum computer. Okay, but we couldn't just say, look, it's Sharp-P complete, end of story, because we needed to show that the actual observable consequences already encode hard computational problems. Okay, so that necessitated making a more subtle argument. Okay, and that's why we have a paper and not just an observation. Okay, so conclusions. I think that one could imagine worse research agendas than the following. Prove P not equal to NP. Or better yet, prove factoring is classically hard. Can quantum computers solve NP-complete problems in polynomial time? Either, make progress toward building scalable quantum computers, or the even more interesting thing would be to find an obstacle to it. Okay, I tend to be a pessimist and believe in the more boring outcome, which is that we can build quantum computers. Okay? So, can all of physics be simulated by a quantum computer? What about string theory, quantum gravity, even, quantum field theories? Is quantum computing the end of the line, or is there something else even beyond that? Okay, and right now we don't even understand these other theories well enough to be able to formulate that question very well. Okay, and then if you accept this what I called the no super search principle, that there's no physical way to solve these NP-complete and other hard problems, can you actually derive interesting conclusions from that about physics? Okay, so I mentioned a few, but I think it would be fascinating to try to take that further. Okay, so thank you for your attention.